The most common mistake is people not knowing what to do with the lines per millimeter n. Turn it into slit spacing little d, but not before converting to lines per meter n. D equals 1 over n because division tells you the size of each bit. And if n is how many slits there are in 1 meter over n is the gap between the slits. I'm going to explain the diffraction grating formula, which is n lambda equals d sine theta, and do some examples. So the first thing I'm going to do is label this diagram with some key information. So we have light passing through a diffraction grating. A diffraction grating is basically lots and lots and lots and lots of tiny slits. This is very, very zoomed in. In a normal diffraction grating, you might have 300 of these little slits in 1 millimeter of diffraction grating. And over here I have a screen. I'm going to call the distance from those slits, the diffraction grating, to the screen, capital D. On the screen, we see dots of light. We see a central dot, and then we see dots either side and dots even further out. We give these dots order numbers. We call the central dot n equals 0. We call the dots either side of that n equals 1, and the dots either side of that n equals 2. So on my screen over here, this is order 0, these are orders 1, and these are order number 2. I'm going to call the distance between order number 0 and order number 1 y, and I'm going to call this angle between the line to order 0 and the line to order 1 theta. And you can see that if we did an experiment and we wanted to find the value of theta, we could measure the distance between the 0 order and the first order, and we could measure the distance from the diffraction grating to the screen, and we could use trigonometry to find theta by using tan theta equals y over d. Other things to note is how a diffraction grating is given to you numerically. So normally you'll be given the number of lines per millimeter, and that's usually given as capital N. So for example, you could be given a capital N of 400 lines per millimeter, which means in every single millimeter of this diffraction grating there are 400 of these little slits. Now I'm firstly going to turn that into lines per meter to make it into SI units. Now in the formula you'll see there is no capital N, but there is this thing called little d. Little d is the distance between the slits. So it's the distance from the center of a slit to the center of the next slit. That's what little d is. And we find little d by doing 1 over n. So 1 divided by 400,000, which equals 2.5 times 10 to the minus 6 meters, or 2.5 micrometers. That is everything we need to know to understand the formula. So n is the order number, lambda is the wavelength of the light, d is the spacing between the slits of the diffraction grating, which we can calculate from capital N, and theta is the angle between the 0 line and the first line. I'm now going to do some problems. So firstly, I'm going to give you some information and we're going to find the angles of the different order numbers. So the information I'm going to give is as follows. We're going to have n being 400 lines per millimeter, so that's our diffraction grating. And we're going to have light of wavelength 520 nanometers shone through that diffraction grating. And we're going to find the angle of each order number. So we'll start by finding the angle of order number 1. So we'll rearrange the formula. So theta will be inverse sine of n lambda over d. If I put in the number 1 for n, 520 times 10 to the minus 9 for lambda, and 2.5 times 10 to the minus 6 for little d, the angle that I get is 12.0 degrees. You can try that for yourself. If I then do it with n equals 2, I get that theta is 24.6 degrees. If I do it for n equals 3, I get that theta is 38.6 degrees. If I do it for n equals 4, I get that theta is 56.3 degrees. If I do it for n equals 5, I get that theta is math error. That tells me that the greatest order number that I have in my diffraction pattern is n equals 4. But how could I work that out quickly? Rather than having to work out every single n, how could I work out quickly what the greatest order number that I get is? So the way to do that is to realize that in this diagram, the biggest theta you could ever have would be 90 degrees. You can't get anything more than 90 degrees on this diagram, otherwise the light would be going backwards. So we use the formula, but we put in theta is 90 degrees. So this is to find the maximum n. We say theta is 90 degrees. If theta is 90 degrees, then sine theta is 1. So now using the formula, we have n lambda equals d times 1. So n will be d divided by lambda. So we use our d of 2.5 times 10 to the minus 6 and our lambda of 520 times 10 to the minus 9, and we get an answer of 4.8. Now there's no such thing as the 4.8th order number, so we round down, and we therefore get that our maximum order number is n equals 4, which agrees with my calculations over here. Another thing which you could be asked to do is find the wavelength of the light given some conditions. So imagine you're told that capital N is 800 lines per millimeter, and that the third order is found at 79.7 degrees. And we want to find what the wavelength of the light is. Now hopefully you can see that this is a real experiment which could be done to find the wavelength of some laser light. So we use our formula rearranged. So lambda is d sine theta over n. We need to calculate d. So remember, first we turn capital N into lines per meter by timesing it by 1,000. To find little d, we then do 1 divided by 800,000. We then put that number into there. We put the angle 79.7 into there, 3 into there, and that gives us a wavelength of 4.10 times 10 to the minus 7 meters. And again, you can try that for yourself to confirm. So what I've done altogether is started by explaining what a diffraction grating looks like and how we label those dots that we get on the screen. N equals 0 in the center, moving outwards n equals 1, moving outwards n equals 2, etc. I've explained the different letters in the formula, and I've given examples of how you could find the different angles of the different order numbers, how you could find the maximum number of orders in a problem, and how you could use a diffraction grating to find the actual wavelength of some laser light.
The most common mistake is people not knowing what to do with the lines per millimeter n. Turn it into slit spacing little d, but not before converting to lines per meter n. D equals 1 over n because division tells you the size of each bit. And if n is how many slits there are in 1 meter over n is the gap between the slits.